Bafundi, it's me once again. So welcome to our next lesson on electrostatics. So the past two lessons we've just focused on just calculating the net force on linear charges, that is when charges are placed in a linear manner. So today I just wanted for us to have a question where we have got a two-dimensional application of electrostatic forces. So please, I hope that you enjoy the lesson. If you need to pause at any point, just pause. You can try to do the question on your own, do that. And then most importantly, please subscribe to the channel. Make sure that you hit the like button. All right, and please, you can recommend this channel to as many people as possible. Okay, so let's get started. All right, so I got this question from one of my learners and I thought let's just use it as our first example of calculating the net force in two dimensions. So what I did, I just took the question and I just copied it into this pad here because I realized on our last video we had a bit of a challenge with seeing from a question paper. So I'll try and improve on that in the future, but okay, let's take the question and see what to do with it. All right, so we've got point charge X, we've got point charge Y. X is a negative 12 nanocoulombs. We've got point charge Y, which is positive 8 nanocoulombs, and point charge Z, which is 10 nanocoulombs. Now, one of my learners actually asked me a little earlier on what it means for charges to be either negative and positive and so on. So what I'm going to do is I'm going to dedicate a full lesson to just recapping on the grade 11 part of electrostatics so that I can basically just explain everything that has to do with point charges. But for now, just appreciate we've got negative charges, we've got positive charges. For the sake of what I want to teach today, I'm not going to go back on that, but I will explain that in a later video. All right, so here we are, we've got 3 point charges. Definitely, these are not placed in a linear or one-dimensional arrangement, but you can definitely see that they're in 2 dimensions. So first of all, they ask us to draw a vector diagram to indicate the electrostatic forces exerted by point charge X and point charge Z on point charge Y. So essentially, what we want to know is what is the net force exerted on Y by X and Z. Now let's start. So in this case, it means that we're going to focus on point charge Y. So please remember that. Okay, so first I ask myself, here's a question. All right, I'm going to draw that dot there showing my free body diagram or my vector diagram. Okay, so I'm going to ask myself, okay, what type of a force exists between, okay, let me start with X and Y. What type of a force exists between X and Y? Well, we've got X, which is negative, and Y, which is positively charged. So in this case, we know that unlike charges attract each other. So we know X and Y will attract each other. So here's X and here's Y. They're going to attract, pull each other closer. All right, but what's happening? We are focusing on Y. So in this case, what type of force or what is the direction of the force that Y feels because of X? Definitely it is a force to the left, or we can say if we want to use compass points, okay, so that's north, that's west, that's east, and that's south. So I always say we, you know, I always confuse west and east. So just to remember it, I always say we. So this is the way that you'd normally write we. Okay, so in this case, we're simply saying, okay, so here's X and Y. they're pulling each other closer, but we are focusing on y. So we're saying y will go towards the west because of point charge x. So here's the direction that y would be pulled towards because of x. Okay, we agree on that. Right, and then, all right, we forget about x a little bit, and then we focus now on y and z. Okay, what type of a force exists between y and z? So if you look at that, what's happening? These are two positive charges. Okay, so what are they doing to each other? They are actually repelling each other. We know that like charges repel. So they're both positive. So what are they doing? They're repelling each other. So what's happening? They're pushing each other away. So which one are we focusing on? We're focusing on y. So what type of a force, or where would be the direction that y goes, or of what's the direction of the force that y feels because of z? In this case, it would be towards the north. Okay, so what I'm going to do there is I'm going to draw that. So it means that the direction of the force, okay, that y feels because of, so I'm going to call this, so this is the force between x and y, and this is the force between z and y. Okay, now please, I want you to note this. All right, so here is our ultimate direction. However, so what I want us to do to complete the question is to also draw the direction of the net force. Now, many a times, this is the mistake that most of our learners do or make in this case. When you say, all right, show the net force, they would simply connect those two. Now, please remember, the net force should be a force that shows you that shows you where it is that both these forces would actually result, what both these forces would result in as you actually apply them, or as they are applied on y. Now, please, I want you to note this. The only way that you can connect is if your dots, or rather your forces, are actually drawn head to tail. Now look at this. This one is in that direction and this one is in that direction. So there's no way that these two can result in a force in that direction. Okay, so we must find a way to actually draw them head to tail. Now there are two ways. I'm going to show you the two ways in which we can do that. So first of all, what I will do is, let me just redraw this diagram. Okay, right, so I can draw them head to tail. Okay, so I'm going to start with FZY. So I'm not changing anything about its direction. Okay, so that's FZY. And I've got FXY. All right. Now, I'm going to draw FXY at the head. I'm going to draw the tail of FXY at the head of FZY. So it would be something that looks more or less like this. Okay, I'm not using a ruler, so please apologies if my forces look a little bit or my lines look a little bit clumsy. Okay, now look at this. So you're simply saying we've got FZY. I've changed nothing about its magnitude nor direction, so it's going up. Here it is. All right, and at the head of FZY begins the tail of FXY. So going in that direction. I've changed nothing about its magnitude, nothing about its direction. Now look at this. Now to draw the net force, I'm just going to use a different color so that you can see it there. All right. So to draw the net force, I'm going to start at the tail of this one. So you can tell this force and this one put together give you a net force in that direction. Okay, so that is the direction of our net force. Okay, I'm struggling a little bit with my orientation there. Okay, so right, so look at this. Both of these put together give me a net force in that direction. Another way that you could have actually done that is to actually draw a parallelogram, okay, on this diagram here. So I will draw an equivalent. Okay, let me use dotted lines instead. Okay, so I'll use an equivalent of fxy on the opposite. So remember, parallelogram just simply means the opposite sides must be equal. So fxy and that side must actually be equal. All right, and then I've also got another side which is opposite fzy, which is actually equal to fzy. Okay, and then all that you simply do, okay, all that you simply do there is you are going to just simply draw that, and that is our net force. Note the direction of our net force. That and that are exactly the same. So that is how you would draw the net force. So in this case, this one looks a little bit more neater. Okay, and then we know that it's a 90-degree angle. There's a 90-degree angle between fzy and fxy. All right, the one is to the north and the other one is to the west. Okay, so north and west are actually at 90 degrees to each other. So that's a 90-degree angle there. All right, now let's go to the second question. Right, now they say to us, calculate the net electrostatic force exerted by point charge X and Z on point charge Y. Okay, so now they're asking us to calculate that net force there. All right, so just like we did for the previous questions, right, we know now how to apply Coulomb's law, right? So Coulomb's law, we know that the force between 2 point charges or between two charges is directly proportional to the magnitude or to the size of the charges and inversely proportional to the square of their distance apart. Okay, so we know we are looking for, let's start with fxy. All right, so fxy, so it means I'm going to say qx, qy divided by r squared. Okay, our Coulomb's constant, that's 9 times 10 to the power 9, multiplied by the charge on x. You remember that? We said it's minus 12. But remember, I said we don't need to actually substitute that, that minus sign there. Actually, we don't need to substitute the signs. All that we do with the signs, they help us to identify or to find out what the direction of the force is. All right. So in this case, we already have found out, because that was negative and that was positive, we actually found out that y is actually being pulled towards the west. Okay, so let's go back to that. So our Coulomb's constant, that's 9 exponent 9, 9 times 10 power 9, multiplied by q of x, that's 12 times 10. Remember nano yesterday, all right, or previously we said that's times 10 minus 9, multiplied by the charge on y. So what's the charge on y? Charge on y is positive 8 nanocoulombs, but remember we disregard the sign, and all that we simply do is just take the magnitude divided by, what is the distance between x and y? That's 30 centimeters. Now, when you see a distance, or rather something that's given to you in centi, okay, a cent, if you say percent, it's always divided by 100, isn't it? So centimeters, so it means that's 30 centimeters, so you divide that by 100, or you can just simply say times 10 minus 2, okay? So 30 divided by 100, that will give you 0.3, okay? So that's going to be 0.3 meters, all right, squared. All right, so we'll work that out quickly. All right, let's do that. So that's 9 exponent 9 multiplied by 12 exponent minus 9 multiplied x exponent minus 9 divided by 0.3 squared, and that's going to be a terrible figure there. That's 9,6 times 10 minus 6. All right, Remember, that is newtons, all right? And you've already told me that that force is to the west. Okay. All right, now let's calculate FZY quickly. Okay, that's KQZ QY divided by R squared. So let's do that. So that's 9 times 10 to the power 9. The charge of Z is 10 nanocoulombs. So that's 10 times 10 minus 9. That's nano as well. Multiplied by the charge of Y. That's 8 times 10 minus 9. Okay, I'm going to teach you another trick a little later on. Divided by, that's 40 centi once again. So that means you divide that by 100. So that's going to be 40 divided by 100. That gives you 0.4. And please remember to square that. Okay, so I'm just going to, let's see if I can cheat a little bit. You know what, let's just, so that's 9 exponent 9 multiplied by 10 exponent minus 9 times 8 exponent minus 9 divided by 0.4 squared. Okay, right, so we get a figure of 4.5 times 10 minus 6. Okay, remember that's a force and that's in newtons, and we did say that force is to the north. Okay, so that is to the north. Now remember, we're not done. What we are looking for is the net force. So it means that we want to calculate that. Now, as opposed to the previous examples that we have been doing, where we either had to now add the forces together because they were in the same dimension. In this particular case, I want you to please look at it. Okay? Now you've got two forces that are at right angles to each other. Okay? And you're looking for the net force. All right? Now we go back to our mathematical tools. All right? So if we wanted to get, if this is a 90-degree triangle, all right? So we know this side we call the hypotenuse, okay? And mathematics says the square of the hypotenuse will always be the sum of the squares of the other two sides, all right? So what do we know? How do we get our net force in that particular case? So we say F net squared is equals to Fxy squared plus Fzy also squared, okay? Right, so to find out our net force, I'm not going to waste time on this. Okay, so we're going to take the square root, our fxy value, all right? This was fxy, all right? That's going to be 9.6 times 10 minus 6, all right? Squared plus, that's 4.5 times 10 minus 6, also squared. Okay, right, and then let's just work that out quickly. We'll take the square root. Okay, that's 9.6 sorry, exponent minus 6, we know that is squared, plus, that's 4.5 exponent minus 6, also squared. Okay, I get a value of 4.5 exponent minus 6 newtons. Now, of course, you can't just say that direction is, northwest, okay? Because if you think about it, anywhere between north and west, okay, is northwest. Now, usually when they ask you this in the exam, they would just say calculate the magnitude of the force. I've looked at previous question papers. They usually say calculate the magnitude of the force, in which case this would be sufficient. But I'm just taking this a step further. What if you wanted to get the direction? Okay. What if I wanted to find out what is the direction of that force? All right. Now, what I would simply do is that I need to now find out what is the angle between, okay, so that angle there, theta, all right, from the north, okay, so here's my north line, okay, or any reference point. If my reference was to the west, I would still find that angle towards the west. So here's the angle here. I want to find out how far is it from my north line, okay? So what I'm simply going to do, now look at this, I'm going to apply my trig ratios. For those of you who still don't know trig ratios, I'd say you just need to be a little bit worried, but nonetheless, it's something that you can learn, and it's pretty easy to learn. Right, so look at this. So I know the two sides, okay? I also know the net force, but I'm going to stick with these two sides. So in this case, from this angle, where is xy? It's opposite to that angle, okay? And to this one, we know this is always called the hypotenuse, isn't it? So in this case, on this side, fzy is actually next to the angle. We normally use adjacent, okay? So in this case, I've got the opposite side and I've got the adjacent side, okay? So in that case, it means I'm going to use the trig ratio of the tangent, which means the tan of theta. So tan theta, you could have also used any of the other sine of theta would have been opposite over hypotenuse. So you could have used fxy divided by f net, but I'm going to stick with the tangent, right? So tan of theta, that's going to be, remember we said tan of theta, that's opposite, okay? So let me just write it there, divided by my adjacent side. So meaning the tangent of theta is fxy, all right, divided by fzy. Okay, I'm struggling just a bit getting to that side of the sheet. So, right, just going to pull this up a little bit so that you can see it. Right, so tan of theta, what's fxy? My fxy value, remember we said that's 9,6. So that's 9,6 times 10 minus 6 divided by 4,5. It's that value there, times 10 minus 6 as well. Okay, so remember that's the tan of theta. All right, of course we can divide those two by each other. Okay, so they actually give us 1. Right, so now I'm going to simply say 9,6 divided by 4,5. 9,6, if you want to, you can say exponent minus 6. Okay, just in case some of you think I'm cheating you. 9,6 exponent minus 6 divided by 4,5 exponent minus 6. Okay, so I get 32 over 15 there. Okay, you can change it to decimal. That's 2,13. All right, so I'm just going to simply say, remember I'm looking for the angle, so the angle is the inverse tan. Okay, so that's the inverse tangent of those two values, 2,133 recurring. Okay, so I'm not going to remove it here, so I'm just simply going to say shift. Okay, here's my 10, so that's 10 minus 1 there, inverse 10. Okay, that's 2, in fact, let me do this. Let me just say answer so that it's more accurate. Okay, and then I get a value of 64,88 degrees. That's my angle. But now please keep in mind, I now need to give a full expression. They said to me I must calculate the net force. So it means that the net force, okay, remember the magnitude of it, we calculated it there, is 4,5 times 10 minus 6 newtons. Now what is the direction? Okay, now remember in this case, going back to this drawing, This is from my north line. So that is the part, that is the reference direction that I know. So from the north, I actually move 64,88 towards which direction? Towards the west. So from the north line, I move in that direction 64,88 degrees towards the west. So from the north towards the west, 64, what's that? 889, you might want to say. So in this case, I'm simply going to say this is 4,5 times 10 minus 6, okay? Right, and then, so I'm going to say my net force is 4,5 times 10 minus 6 newtons, right? In which direction? From the north, okay? I'm going to move 64,89 degrees towards the west. Okay, right. For those of you who know things about the bearing, okay, you could have also calculated the bearing, but that's another story from another day. But remember, to calculate bearing, you always need to take it clockwise from the north line, all right? Clockwise from the north line. So in this particular case, this is at north, 64,89 towards the west. I hope that makes sense, ladies and gents. So that is how you actually do a question in 2 dimensions. I think perhaps it would be fruitful if we did another question, but we'll do that in another session. Okay, thank you so much.